Of course, it's my great pleasure to introduce Luca Bertello. And Luca collaborated with us, with our solar physics staff, in particular with Bruno Caccin, in the late 80s, early 90s, so more than 30 years ago, Luca.
Yeah.
Yeah, probably, if I remember well, during your PhD thesis. And where he did basic research on observations and modeling of solar acoustic oscillations. After this period, he spent more than 10 years at the Department of Physics and Astronomy of UCLA in Los Angeles. And then he moved to the National Solar Observatory, where Luca is currently a full scientist. Luca is involved in various synoptic programs, in particular long-term investigation of the sun, and he has a long experience, you understand, more than 30 years, with a broad range of solar observations, data reduction, and analysis techniques. So today we are grateful to have Luca back to present at the seminar, Understanding Solar Variability in the Context of Space Weather. And thank you, because for you it's early morning, not afternoon. So
very early.
Thank you.
No, of course.
And please go.
Okay, thank you, Francesco, for the nice introduction. So today I'm going to talk about solar variability and space weather, two topics that are obviously closely related to each other. Now, while solar variability has been studied for over a century now, space weather is a relatively young research area. It is virtually impossible to convey a comprehensive description of these two topics in a single talk. So what I'm going to try today is to sort of give you a general overview about some of the most important facts for both topics. Okay, so in a nutshell, this talk will address some of the following questions. So what is space weather first? So what we mean really by space weather? What causes space weather? What are the technological impacts of space weather? What can we do to protect against space weather? And then at the end of the talk, I will probably spend a few more minutes, additional minutes, about sort of talking a little bit about the impact of space weather on climate and habitability of terrestrial type exoplanets. It's not really my area of expertise, so I'm just going to give you some few information really about this topic. Now, the short answers to those questions are listed here. So definition of space weather is kind of tricky. So from a general point of view, we can say space weather are essentially the condition in space that can affect satellite and technology on Earth, and of course as well human life and health. What we know about space weather is that the main cause is obviously the sun. Hello? Oh, the cause of space weather is the sun. There is, in general, also a little contribution from extragalactic cosmic ray, but the impact of those are kind of limited. So the main source is really the sun. In terms of technological impact of space weather, well, we know today that solar events will affect GPS, power grids, and telecommunication. What can we do to protect against space weather? Well, mostly is about research, then is monitoring, because we have now capability to actually monitor the sun on a regular basis. And probably the most important case is to understand what happened in extreme situations. The impact of space weather in other stars, especially in exoplanets, is not really something we know much about it today. It's a new field, and so there is still a lot of study that need to be done. So let me give you first the study of space weather is obviously a very important topic in the US, and the agency which is responsible here to actually do that is the National Research Council of the, well, is NOAA. I'm going to talk more about that later on, but the history of space weather in the US basically started in 2008 with the publication of an important document by the National Research Council of the National Academies. This document was motivated by the October-November 2003 series of solar storms, which are known also as the Halloween storms. These storms have caused severe and costly damages, and they are also suspect to have caused the loss of a spacecraft, which was about $640 million loss. It is also the first official document from the US agency that bring attention to the importance of space weather. This is actually a very comprehensive document. It basically describes the impact of space weather in retrospect, and also the impact of space weather in society, and describe also to some degree the current infrastructure and the possible solution, vulnerability and risk caused by a space weather event. At the end of the document, basically, there is this conclusion, which is described here, which kind of highlights the importance of this kind of study and sort of define, to some degree, the concept of space weather. So modern society depends heavily on a variety of technologies that are susceptible to the extremes of space weather disturbances of the upper atmosphere and of the near Earth space environment that are driven by magnetic activity of the sun. To understand the impact of space weather, we can look at this infograph here. Basically, there are different effects as a result of some strong event. Well, let me go through here, the mouse, yeah. So one of the first impact is on the electric power grid. So strong induced current can disrupt and damage modern electric power grid, and may contribute also to the corrosion of oil and gas pipeline. Magnetic storm driven also produce interference with high frequency radio communication and signal from a GPS satellite, which is sort of kind of visualized in this picture here. There is also a possible impact on communication along transport or aviation routes, requiring aircraft to fly at lower latitude. And you have to keep in mind that this is a big deal for airline company, because typically rerouting flight costs airline anything between about $10,000 and $100,000 per flight. So, you know, it's not something that they can take lightly. Another possible potential issue is that the space weather can produce energetic particles during solar energetic events that affect the radiation belt and can cause temporary operation anomaly and damage critical electronics. And these also include not only satellite, but include also, for example, the situation for astronauts during their extravehicular activity outside. There was an episode during the Halloween storm where that could have been potentially a damaging effect to the astronaut. There's a slide here. Now, I'm going to give you sort of a little bit of history here. The probably most famous space weather event on record is the 1859 Carrington event, which was named after the British astronomer Richard Carrington. And at the time, obviously, they didn't know much about the connection between solar flares and geomagnetic storms. But for some reason, Carrington was actually looking at the sun at the time and realized that during the strong geomagnetic storm, he noticed a very strong, intense white light flare, which was associated with the geomagnetic storm. So on this right here, you can see the regional drawing by Carrington. And what you see here is the typical example of a sunspot group. So those are basically sunspots. And if you look closely, you see those two white kind of features, which are basically the location that correspond to the location of the solar flare. This is by far the strongest event that has been recorded and happened basically during almost a week between August 28th and September 4th in 1859. It produced several kind of display, particularly the aurora at very low latitude, like in the Caribbean, in Florida, and in the southern hemisphere. Aurora was seen also in Santiago, Chile. Not to mention that it also produced a disruption of telegraph services around the world. But this connection, this is something I like to emphasize now. So this connection between the geomagnetic storms and the actual solar event wasn't really put much into a connection, into attention. After the Carrington event, there were other important events that affected basically several tools here on Earth. This is not in particular order of strength, but is mostly in terms of date. The famous 1921 geomagnetic storm, which also disrupted several telegraphs and utilities on Earth. And there are some sort of information from newspaper at the time that is kind of describe the effect of this storm. May 21, 1921 was already a time where people realized the connection between the sun and the geomagnetic storms. Then there is the famous 1989 blackout in Canada, which is kind of highlighted here on the low figure, which produced damages that cost more than about $30 million. This was the estimate at the time, and sort of produced a blackout that lasted for 9 hours and affected several million people. One of the, and this is basically where the sun starts to play a role here. There are different types of solar activity that are associated with the space weather, and they can divide it mostly into 4 different components. 2 of those components are shown here, and those are the solar flares, coronal mass ejection, high-speed solar wind, and solar energetic particles. If you look at the left side of this slide, sort of give some sort of description of what a solar flare is. Solar flare impact Earth only when they occur on the side of the sun facing Earth. And they are typically produced from sunspot groups, but from location where you have a complex groups that basically at some point something happened in the group that produced the release of a lot of energy. And typically the important wavelength range for solar flare is the X band, is the X-ray band. They travel directly from the flare site to Earth, and so it basically takes about 8 or 9 minutes to reach the Earth. Coronal mass ejection are also known as CMEs, and are basically essentially explosions on the sun with the corresponding release of plasma and magnetic field that erupt typically from prominence. They can erupt in any direction. So basically, after they erupt in a certain direction, they essentially continue on that particular direction into the solar wind. So unless the CME erupt in the direction toward Earth, then the Earth won't be affected by that. However, if the direction is just right, then you can expect extreme space weather happening and extreme disruption on facility on Earth. So those two images, the one on the left shows the halloween flare, October 2013. We have in solar physics a way to classify flares in terms of their X-ray emission. A X-class flare is the strongest class of flare, and halloween flare was a X12. I'm going to go back to that at the end of my talk. On the right side, you see the July 2012 CME event, and you can really clearly see the extension and the magnitude of the event. There is if you can see that, there is the size of the Earth to scale. So these are extremely strong solar events that are the main cause for space weather, essentially. High-speed solar wind streams comes from area on the sun known as coronal holes, and these holes can form anywhere on the sun, and usually only when they are close to the solar equator do basically produce some impacts on Earth. On the other hand, the solar energetic particles are high-energy charged particles, and they are released by shock formed at the front of CMEs and solar flares. So they are mostly associated with CME and flares. And basically, they go into the solar wings. They have high velocity, and they are very energetic, and then they can interact with the Earth magnetic field and produce, again, some serious impact on Earth. So those events are basically and typically follow some sort of chronology. So there is a three-phase chronology of those events. Basically, what happens is they typically are produced by complex sunspot groups. And we could talk about that for hours, but what happens is usually this group rotate into view from the eastern side of the sun, and at the beginning they generate not very strong solar flare and typically slow CMEs. Slow CMEs are typically referred to these events when the speed is less than 800 kilometers per second. Now, as the sun rotates, so the sunspot groups start to go closer to the center of the disk, you can have additional event and some X-ray, some X-class flare and fast CME with speed greater than 800 kilometers per second. So at this stage, the fast CME, because of the orientation, will probably miss Earth, and you don't expect to have extreme geomagnetic storms. The critical phase is phase 3, when the CME is actually directed in the same direction as Earth. I can hear some background noise. I don't know if somebody is trying to ask a question or not. I don't see the chat, so.
I muted. No, there was just someone.
Ah, okay.
An open mic. Sorry about that.
No, that's okay. I was just wondering because I'm not very familiar with Microsoft Teams, so I don't know what's going on the background. So during phase 3 is where really things happen on Earth, and the duration from the time the CME erupt and it reach Earth is typically in the order of few days. So it doesn't really take much time to impact Earth. So those now has been known for quite some time, and in the US, the major agency in charge of sort of taking care of these issues, National Oceanic and Atmospheric Administration, which is typically referred simply as NOAA. And there is a long study that was published by NOAA about kind of distinguish between different solar events and their impact on Earth. They came up with essentially 3 types of events, which are listed here. Geomagnetic storms, which basically are produced by high-speed solar winds and sometimes also CMEs. They measure this kind of event or this kind of storms with what is known as the planetary K index, or simply the KP. Then you have the solar storms, solar radiation storms, which are mostly produced by CMEs and solar flares, and essentially consist of high-speed protons that become part of the solar wind. The intensity of those storms is measured in terms of the proton flux level in mega electron volts. And finally, the radio blackouts, which is mostly due to solar flares. And there is a satellite that is managed by NASA, which is GOES, which is in charge of monitoring the intensity of solar flares, which are measured in X-ray flux, essentially. There is a traditional way to divide flares in terms of classes, and those classes are listed here as A, B, C, M, C, and X, where A are essentially flare with a very low level of emission, and X is the class that contains the strongest solar flares. Now, I'm not going to go through these in too many details. The only thing I want to point it out is the third column here. But those are essentially the scale corresponding to those 3 events. So shown here is the scale for the geomagnetic storms. And you see they are listed as G1, G2, G3, G4, G5, with G5 contains essentially the strongest event, and below you can read essentially what you can expect from this kind of event in terms of power system and other systems. What is interesting here is the frequency of occurrences of this kind of event. The frequency is measured in terms of number of events per cycle, where for cycle, we typically use as a unit 11 years. And there is a reason about using 11 years. I'm going to talk about that in a few slides. But you can see basically that minor events happen pretty much all the time over a 11 years period, more than 1700 typically per cycle. But extreme events are kind of rare. They are typically one every 3 years. So it's not common, but obviously the impact is significant anyway. The other scale is the one for the solar radiation storms. And again, those are less frequent than the geomagnetic storms. So you have about 50 minor events per cycle. And really, fewer than one event per cycle for the extreme case. And if you look at the description for the effect of a S5 event, you see there is essentially a hazard for astronauts. And this is basically the most important event for aviation, because that's what is going to cost the airline basically for rerouting their flight from higher latitude typical polar routes to lower latitude. There is a significant impact also on satellite operation, and essentially data will be contaminated, and you can have also significant damages on the solar panels of satellite. And high frequency communication will be affected, and also GPS will be affected in these particular cases. There was I remember reading during the first Gulf War in Iraq, there was a solar storm that actually blacked out military communication for several hours at a time. And you can imagine this really caused a serious concern, because it was in a critical situation, and so to lose communication, well, it's not really something that you want to deal with it, especially in the military. They're very sensitive to these things. And that's the other thing. So most of these kind of research and monitoring are also, at least in the US, are also supported by military operations. And we actually receive a lot of feedback from, in my case at least, from the Air Force branch of the military, which is obviously in Platt. The last scale, it's a radio blackout. Again, not many not many events at low scales, F1, R2, or R3, but extreme events are also not very common, just one per cycle. Those kind of blackout, and I remember this is basically produced by solar flare. They typically produce high-frequency radio blackouts, and obviously they produce difficulties for navigation, and especially for the general aviation that will suffer from outages, and satellite will be also strongly affected by these things. Now, extreme events are so basically typically in the order of one per cycle or less. Having said that, those are not like the Carrington event. There's been a lot of study recently about the Carrington event, because if something like that happened today with the kind of technology that we are running, obviously the impact will be much more devastating than what happened back in 1859. So the latest study suggests that basically an event like the Carrington geomagnetic storm is likely to happen once every 100 or 200 years. So we are almost due for another Carrington event. Now, let's go back to the sun. So this is what happened essentially on Earth as a result of the sun. But what produced those solar events that are impacting our life on Earth? Well, those events are related to what is known as the cycle of solar magnetic activity. And this figure illustrates this cycle of activity. It shows a sequence of EIT 3 or 4 Armstrong images of the sun taken each year from 1996 I lost the amount. Okay, from 1996 to 2006. So the sequence covers what we know is considered to be one solar cycle. This is, in this case, we are talking about cycle 23. So 1996 is the beginning of the cycle, and then we go to 97, 98 until we reach 2001, which corresponds to the maximum of solar cycle 23, which is also when basically the sun was the most active. And then again, we go down until we basically end in 2006, which corresponds to the end of cycle 23. So if you look at this image, you see basically the level of activity change quite a bit between period of minimum and period of maximum. Solar events are typically happening more frequently during period of maximum activity. So you expect more of the event I described before during period like 2000, 2001, and 2002. There are also situations, however, where you have strong event during period of lower solar activity. So although the frequency and the probability is higher during period of maximum activity, you can expect some strong event also during period of lower solar activity. Now, this image of this series of this level of activity in the extreme ultraviolet is only one kind of manifestation of solar activity. So you know that extreme ultraviolet radiation is absorbed by the upper atmosphere. So it is impossible to measure from the ground. So you can only measure EUV essentially using rockets and satellites. So this, of course, limits the use of this observation for a very long-term study of solar activity. So for this purpose, the study of sunspot has provided a timeline of solar activity history covering essentially more centuries, basically almost 4 centuries. So if you want to investigate solar activity over a longer period of time, then you want to use a different type of indicator, and sunspot are probably the features on the sun that has been visible for much longer than just, for example, the extreme ultraviolet radiation. The history of sunspot observation is actually quite interesting. Sunspot, believe it or not, has been observed for more than almost 2,000 years. At the beginning, the only possible way to observe sunspot was essentially by naked eye, and this is possible if you have particular very good sky condition, which kind of reduce the intensity of the solar disk, and so it can be visible. During the early 16th century and 17th century, they start to use what are known as camera obscuras, and we have basically the very first observation of a sunspot made by Kepler on May 28, 1607. But the game changer was obviously the invention of the telescope, and that's when basically we start to have a better understanding of at least the morphology of those features on the solar disk. The earliest known working telescope was appeared basically in 1608, and there's some sort of debate about who actually invented the telescope, and the tendency now is to credit the invention of the telescope to Lippershey, and somebody still think that maybe Galileo Galilei was the first to invent or to create the telescope. I'd like to review some of the properties of this observation. There are records of sunspot observation that going back to basically almost 400 BC. And those are available in some of the star catalog, which are present in the Chinese astronomer Gan Di. And by 28 BC, those observations were actually recorded regularly, and they produce what are known as the imperial records of documents. So, and these are available actually, some of them are actually available online. There is a large number of also historical naked eye sunspots, which are mostly being reported from Korea, Japan, and Europe and other countries. Most of these investigations about these old measurements have been done by Vaquero, which has spent a lot of time going to different churches and other facilities, and he made a important analysis of all these kind of observations. There is an important paper which was published by Vaquero and Gallego in 2002, which I strongly recommended to read. It was kind of interesting history of how you recover these kind of observations. Now, the probably most important compilation of this observation was published in 2003, which kind of report a summary over time of this observation. I'm going to show you now the result. Both Vaquero and Vigilant also published similar results. I'm going to show you the result from Vaquero. You can probably ignore the top plot, which is probably not relevant for now. But this is basically a number of sunspots recorded by naked eye observation. And you see, they cover basically almost 2,000 years of observation. The number goes from 0 to 0.8, mostly because, for whatever reason, Vaquero decided to apply a running mean, 50-year moving running mean through the data set, so that reduced the number. In general, those numbers are in the order of few for each year. Typically, they go about, between 5 and 20 in the original file. But what is significant in this figure is the presence of a period where basically you really don't have a sunspot present on the disk. At least they were not recorded. And they are kind of named from famous guys. So you can the Sporet minimum, Wolf minimum. There is a medieval maximum here. And probably the most, from a historical point of view, the most important minimum is known as the Maunder minimum, which is which happened in the second part of the 17th century. I think I need to go a little bit faster now. In terms of observation done with the camera obscuras, I probably just need to mention that they basically cover the 17th and the 18th century. There is a lot of observations were taken in Bologna from the cathedrals. There is a description of how the observations were taken. They were able, these observations were able not only to show the presence of sunspots, but they also actually measure the diameter of the sun. And there is a time series of these observations about the diameter of the sun that cover almost 100 years of measurements, which also were investigated by Vaquero. From a historical point of view, this is probably the first drawing of a sunspot. It was published in 1128. This guy was a monk, and he's most famous for publishing a book about the history of humanity. But you can see in this figure, those are two sunspots on the solar disk. And obviously at the time they didn't know anything about the nature of those features, but you can clearly see the umbra, what we know today as the umbra and then the penumbra of the sunspot. So it's kind of interesting to see that even at the time they could actually see something about the morphology of the sunspot. And this basically is the start of the telescope era, and this is the first publication by Fabricius, where he reported the observation of sunspot using a telescope, almost at the same time that Galileo was making his observations. And I really need to show this drawing from Galileo because it's just beautiful, and you can see the details of the sunspot. You clearly see the umbra and the penumbra, and this observation was made in 1612. He actually made an observation for several days, and he also noticed that those features were moving, which means, the sun was actually rotating. So that was a significant finding from Galileo. It takes almost 200 years, or well, less than 200 years, to figure out that the number of sunspots basically that appear on the solar disk basically follow some sort of cycle. And the first report of existence of what we know today as a solar cycle was made by Schwab. And here is basically the important result that clearly show the existence of the solar cycle. So you have on the x-axis you have here, on the y-axis you have the number of sunspot group, and you can clearly see basically that the number of sunspot group increase about, reach a maximum about 1828, 1829, then the number decrease and then increase again and reach another maximum about 1837. So this was basically the beginning of the study basically of solar variability, if you can say that. However, it was only on 1908 that we understood the actual nature of sunspot. That's basically due to the famous paper by George Hale, where we sort of realized that those are actually a magnetic feature. And this is also another paper that I recommended to read because it has a very nice description on how he come up with the answer in terms of saying that basically sunspots are active regions. So this is the beginning of study of solar magnetic field, basically. That's what it is. Critical paper by George Hale. We know, obviously, today a lot about solar variability and particularly about solar cycle. This is kind of a summary of the different cycles over time managed by called the International Sunspot Number. It's kind of weird the way they define sunspot number, basically by adding individual numbers of sunspots to group of sunspot multiplied by 10, but it's been like that basically from the very beginning. There are reasons that I'm not going to go through for this kind of definition, but so in the top plot you see basically they have kind of a consistent observation beginning from 1700. And then you see the separation between the gray area and the blue area. This is basically when we start to count solar cycle. So this is the beginning of solar cycle 1. Today we are probably at the beginning of cycle 25. So if you look at this kind of behavior, you see there are typically a period of maxima which are alternated to period of minima. The height of those maxima change from one cycle to another, and also the shape and the slope of those cycles is different. So this is kind of well understood today. Duration of the cycle varies from around 100 months to 168 months. And there are also other important connections between the property of cycle and as measured from sunspot number. So this is one typical correlation that sort of give us idea about what produce those kind of activity, those kind of cycle of activity. So there is a clear correlation between the amplitude of a cycle and the period of the previous cycle. So this was published by David Hathaway, and but it's been known now for quite some time. So typically what you see here is the longer is the duration of the cycle, the smaller is the expected amplitude of the next cycle. So shorter cycle typically will produce future stronger cycle in amplitude. So sunspot number is one way to characterize the solar activity. Another way is to actually look at the location of activity during the different phases of a solar cycle. Typically, at the beginning of the cycle, you see activity excuse me, at higher latitude. And as the cycle progresses, then the activity goes down at lower latitudes. And this typical of behavior as shown in this plot. And this is true for sunspot with the different areas. So it's very consistent. So it doesn't matter, you know, the size of the area of the sunspot. Basically, they all follow similar behavior very consistently. And you can group all this observation into a single diagram, which is solar physics as is typically referred as a butterfly diagram. And you can clearly see here, these are basically individual cycles starting from 1870. And you can clearly see the trend. So at the beginning of the cycle on the north hemisphere, you start here. On the south hemisphere, you start again at lower. So activity is confined between about 30 degrees north and 30 degrees south latitude on the sun. And then at the beginning, you go from higher, and then at the end of the cycle goes, and then you start again, over again, and so on and so on. And you see the cycle is about 11 years. One thing that I should probably mention, because it's important, is that polarity are typically reverse on every 22 years. So in a typical cycle, you're going to see the leading polarity in a sunspot group in one hemisphere and the opposite leading polarity in the other one, and then they reverse on the next cycle. So the magnetic cycle is really 22 years, not 11 years. But unfortunately, I don't have really much time to do that. So that's another important correlation between the actual sunspot number versus the area of sunspot, and it's clearly very linear correlation. In general, I don't like to use the sunspot number as a physical quantity because it's not. And I always use, for example, sunspot area instead. But, you know, this kind of result to some degree validate the meaning of the sunspot number. Property of sunspot are just one of the indicators of solar activities. There are other indicators which are currently used to characterize solar activity. A summary of those indicators are shown in this image, in this figure. So on top you see the sunspot number, which is basically the one that produced the longest time series of solar activity. But then you have also the 10.7 flux, and you have the Lyman alpha measurement, calcium K index, and then the magnesium 2 index. The bottom line is that on time scale of several months or comparable with the period of 11 years, all these indicators show the same pattern. So you see those lines here are average or running mean of those measurements. So they really show pretty much the same thing. Things are different at the shorter time scale, but this is one of the important aspects that we are trying to understand. So the difference in time scale shorter than a month between these different indicators. I'm usually more focused personally to study the calcium K property because of the chromospheric response to that particular line. So why all these things is important? Well, what we do in solar physics, or what many people do or trying to do, is to understand what produces this sort of variability. And we know that this variability is produced by a kind of dynamo mechanism. We don't really know much. I mean, we know some of the properties. We can reproduce some of the observations, but there are many observations that we cannot model properly, at least at the present times. So all these properties, like this behavior that is shown here, are actually constraints to those models, and they are used to sort of make the physics of those models better, because you try to really reproduce what you are observing. That's the critical thing. And a good model will also produce a possible possible forecast for solar storm events that obviously affect space weather. So this is one of the key research, for example, conducted by NOAA in the US, which is basically trying to predict in advance the occurrence of these storms. And to predict in advance the occurrence of these storms, you need to have decent models. And decent models are constrained by observation. So it's very much all together combined. So this is about the sun and about essentially space weather and impact on Earth. Things are quite different when you look at other stars. And we know that other stars can be also very active. Actually, in general, more probably active than the sun in several cases. Now, the interest of space weather in other stars, mainly due to the discovery of exoplanets. And I think the first, I'm not an expert on this area, but I think the first detection of an exoplanet was done in 1992. And since then, especially because of the Kepler mission by NASA, they discovered a bunch of other exoplanets. And I think this figure shows the result as of December 14, 2017. At the time, the total confirmed number of planets was 3567. 25, little bit more than 2,500 was from the Kepler mission, shown here basically in yellow, as a yellow dots, and other missions that produced the discovery of those other dots. I checked recently, and today, I think as January 2020, the number is more than 4,300, so it's increasing, let me put it this way. So what is significant about this figure is basically, if you look at the location of these dots, you can clearly see that there is in terms of size, there is a bunch of dots which are kind of located around 1, so solar radius. There's other that have a larger radii, size of Neptune or the size of Jupiter here. So there is a bunch of possible planets that could allow for life on Earth. One thing I wasn't really able to appreciate much was, when I first look at this plot, give me 5 minutes, I'm done. When I look at this plot and I check for the orbital period, the orbital period of the Earth around the Sun is 365 days. So when I look at this, this plot, I see orbital period of, in the order of 10 days, for example. So those are very fast orbital rotations of those planets. So that would kind of surprise me, because so used to the Sun that, this number is kind of quite different, I would say. So this is pretty much a blowout of the previous plot, basically, where it shows essentially some of the candidates that are within a possible region of what they call the habitable zone for planets. And so there are really a lot of possible candidates. And so temperature is comparable with the temperature of the Sun. Energy, I think the scale is in terms of comparison with the energy received by the Sun for the Earth. So there's a bunch of possible candidates that could, in principle, allow for life. Now, one feature, and just last night I was reading a study that was published a few years ago. I mean, one difference between some of those stars that are hosting those planets and the Sun is that some of those stars actually show the presence of what they are called very strong superflare. Now, typically, in the case of the Sun, a strong flare releases energy in the order of like 10 to the 30 ergs. Some occasional X-class flare release energy up to probably 10 to the 31st ergs. The Carrington event was estimated to produce an energy, to release an energy in the order of 10 to the 32nd. Now, some of those stars here release flares, release energy that go up to 10 to the 36, 10 to the 38. So we are talking about essentially 5-6 order of magnitude higher than the Carrington event. So we are talking about extremely active event. And this obviously, has several implications in terms of possible existence of life on this planet. Think about the amount of radiation. I think I'm pretty much running probably out of time, so I'm going to stop here. So thank you.